In this lesson, we are going to talk about solving trig equations. So when we solve trig equations, what we are trying to do is find the angle or angles, there might be more than one answer, that makes the equation true. So we are trying to find the angles that make the equation true. And to do that, we want to try and isolate the trig values. So let's look at our first example, tangent squared of x equals 3. So we have tangent squared, and to undo the square, we're going to take the square root of both sides. So I have the square root of tangent squared x equals the square root of 3. Notice we did the same thing to both sides of the equal sign. Then the square root of tangent squared is the absolute value of tangent of x. And the reason that's true is because the square root is not negative. So we have tangent of x has to equal, the absolute value has to equal the square root of 3, which means that tangent of x either equals the square root of 3 or tangent of x equals the negative square root of 3. And there are 4 places where these are true. Either x equals pi over 3, 2 pi over 3, 4 pi over 3, or 5 pi over 3. And you might be saying, hey, how do we know those things? Well, it's important for us to know the trig values for all those common angles. In this section, the problems are going to be set up to relate to those nice angles. So here's our unit circle. If I look at the angle of pi over 3, the corresponding point is the point 1/2 square root of 3 over 2. And remember, tangent equals sine of x over cosine of x. And so square root of 3 over 2 divided by 1/2 simplifies to the square root of 3. And then the other places have points that are similar. In the second quadrant is where the angle is 2 pi over 3, and that's the point negative 1/2 comma square root of 3 over 2, and that has a tangent value equal to negative square root of 3. Over in the third quadrant, we have both x and y being negative, and so tangent is positive square root of 3. And then in the fourth quadrant, we have a positive x value and a negative y value. And so we get tangent is negative square root of 3 there. So again, recall the trig values for the common angles. And on our next slide, I'm going to write those down. So here are the trig values for common angles. You should be able to create this table from memory without using decimal approximations. So the common angles are 0, pi over 6, pi over 4, pi over 3, and pi over 2. And here's the cosine values that correspond to those angles. Remember that pattern. And then for sine of theta, that pattern just goes in the reverse direction. And tangent equals sine of theta over cosine theta. So I just need to take the ratio of our two columns, and we find that tangent of 0 is equal to 0. Tangent of pi over 6 is 1 over the square root of 3. And that's the same as, if I rationalize the denominator, the square root of 3 over 3. Tangent of pi over 4 is equal to 1. Tangent of pi over 3 is equal to the square root of 3. And tangent of pi over 2 does not exist because our denominator would be 0. So in our last problem, we were trying to solve tangent of theta equals the square root of 3, which means that the reference angle is pi over 3. And we look at the value of tangent in all 4 quadrants that has a reference angle of pi over 3. And that's how we got our answers of pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. So let's do another example. Solve 2 sine of x plus 1 equals 0. So we want to get the sine of x by itself. So we subtract 1 from both sides of the equal sign, and we get 2 times sine of x equals negative 1. Dividing both sides by 2, we get sine of x equals negative a half. And now we want to think about our common angles. Sine of pi over 6 equals a half, but this is just telling us that our reference angle is pi over 6. But we want to solve sine of x equals negative 1/2, and that's a negative number, which means that we are looking for an angle that gets us into the third or the fourth quadrants and still has a reference angle of pi over 6. And so one solution is pi plus pi over 6, which is 7 pi over 6. And another solution is 2 pi minus pi over 6, which is in the fourth quadrant, and that's 11 pi over 6. So our solutions to this equation, 2 sine of x plus 1 equals 0, is either 7 pi over 6 or 11 pi over 6. Now, another type of equation that we'll see are quadratic-like. And here is an example. 2 sine squared of x minus 3 sine of x plus 1 equals 0. This is called quadratic-like because it looks like 2 times something squared minus 3 times the same something plus 1 equals 0. And we can solve these quadratic-like equations using the quadratic equation. And so the quadratic formula is when we are trying to solve ax squared plus bx plus c equals 0. But it doesn't matter what this input is, as long as the stuff inside the parentheses are the same. And so we get sine of x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So we get sine of x equals 3 plus or minus the square root of 9 minus 4 times 2 times 1, all divided by 2 times 2. And so this is 3 plus or minus 1 divided by 4, and I end up with either a half or 1. So when does sine of x equal a half? That is when x equals pi over 6 or 5 pi over 6. Again, the reference angle is pi over 6, but because sine of x is a positive a half, we're either in the first quadrant or the second quadrant. Or we have sine of x equals 1, and there's only one place where sine of x equals 1, and that's at x equals pi over 2. So we have 3 solutions to this equation. X equals pi over 6, x equals 5 pi over 6, or x equals pi over 2. Now, I'm going to show a graph of y equals 2 sine squared of x minus 3 sine of x plus 1. These 3 points, these 3 x values, are the places where the graph crosses the x-axis. So here is the graph of 2 sine squared of x minus 3 sine of x plus 1. And we can see there are 3 decimal places where the graph is crossing the x-axis in this view. The first one is at pi over 6, the second is pi over 2, and the third is 5 pi over 6. A calculator is only going to give us decimal approximations for where we cross the x-axis. And so it's important, again, to know the common values for our trig functions, the trig values for the common angles. Let's do another example. Solve 2 sine squared of x plus 3 sine of x minus 2 equals 0. So we get sine of x equals negative 3 plus or minus the square root of 3 squared minus 4 times 2 times negative 2, all divided by 2 times 2. And when I simplify this, I get sine of x equals negative 2, or sine of x equals a half. Now, sine of x equals negative 2 has no solution. And this is because sine of x is always between negative 1 and 1. So sine of x equals negative 2 has no solution. Then we also have sine of x equals a half. We've solved this before. This happens when the reference angle is pi over 6. And because sine of x is a positive number, I know that we're either in the first or the second quadrant. And so then we have x equals pi over 6 or 5 pi over 6. Another way that we can solve trig equations is by factoring, or as I like to say it, unmultiplying, rewriting our expression as a product. Now, quadratic-like equations can be factored, but I think that using the quadratic formula is much slicker. So for quadratic-like equations, I would recommend just keep using the quadratic formula. But what if we don't have a quadratic-like equation? Then we're going to use a technique called factor by grouping. And this is when you have what you guys are going to see, 4 terms, so I can group them in pairs. So 2 tangent of x sine of x plus 2 sine of x minus tangent of x minus 1 equals 0. Notice that there are 4 terms here. And if I group the first 2 together, they have in common 2 sine of x. And what's left over is tangent of x plus 1. The last 2 terms, negative tangent of x minus 1, that has a negative 1 in common, and what's left over is tangent of x plus 1. And so now I see 2 terms, and they both have a factor of tangent of x plus 1. So this simplifies to tangent of x plus 1 times the leftovers, 2 sine of x minus 1 equals 0. So that means tangent of x plus 1 equals 0, or 2 sine of x minus 1 equals 0. Tangent of x equals negative 1. That happens when x equals 3 pi over 4 or 7 pi over 4. The reference angle for tangent of x equal to 1 is pi over 4, but tangent of x is a negative value in the second and the fourth quadrants. Then 2 sine of x minus 1 equals 0 means sine of x equals positive a half, and we've solved this a couple times already. So x equals pi over 6 or x equals 5 pi over 6. So this one has 4 solutions: 3 pi over 4, 7 pi over 4, pi over 6, and 5 pi over 6. And let's do another last example together. 4 sine cubed of x plus 2 sine squared of x minus 2 sine of x minus 1. Grouping the first 2 terms together, they have a 2 sine squared in common, and what's left over is 2 sine of x plus 1. And then the last 2 terms have a negative 1 in common, And again, we've got in the parentheses 2 sine of x plus 1. Factoring that out, we get 2 sine of x plus 1 times 2 sine squared of x minus 1 equals 0. And whenever you have a product equal to 0, one of those factors has to be 0. So either 2 sine of x plus 1 equals 0, or 2 sine squared of x minus 1 equals 0. Solving, we get sine of x equals negative a half, which means x equals 7 pi over 6, or 11 pi over 6. And 2 sine squared of x would have to equal, minus 1 has to equal 0, which means sine squared of x equals a half, which means the absolute value of sine of x equals the square root of a half, which means sine of x equals square root of 2 over 2, or negative square root of 2 over 2. And that happens at our pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So there are 6 solutions to this equation. And that is how we are going to solve trig equations. It's really algebra, working on isolating our trig values, and then using our knowledge about the trig values for common angles.